All right, welcome to 4.2 Math 31 maximum and minimum values. We're going to start to actually use what we basically the sign charts and determining points where the derivative is zero or positive or negative, increasing or decreasing, we can use within the context of functions to talk about their maximums and minimums. So in your notes, you have this, and it is a bit of a kind of big chunk of paragraph for sure. The key words I think here, absolute and local. So if we look at absolute, be it minimum or maximum, those are points that are larger or smaller than the entire function, or basically the highest point in the domain given. And that's going to be something that's really important. When we talk about the domain given, we won't always be looking at x as an element of the real. We might be looking between, maybe just 0 and infinity if it was a time function dealing with velocity or something like that. So you have to make sure you read the domain in the questions. The other word there, being local, is referring to the points nearby. And it's one of those things that, and I'll just draw a cubic at the bottom here, that if I drew y equals x cubed, or a version of, I'm going to transform it a little bit. Looking at this graph, if I were to look at the entire function from, x as an element to the real over the domain, this graph does not have any absolutes, because the range of this graph is y exists from negative infinity to positive infinity, and y is an element of the real. There is no large number. There's a concept, the idea of infinity, that's so large, but that's not a number itself. Now, if I restricted the domain, so if we talked about that same graph, but in between these two discrete endpoints, now we do have an absolute min and an absolute max. This would be our absolute max, the highest point in referring to the output, the y-axis, and this would be our absolute min. Now, with that local conversation coming in, on both these graphs, we have local mins and max. This would be a local max. This would be a local min. And they would actually be in the same location. I mean, I suppose it's a different function because I drew it a little bit differently, but we would have a local max and a local min, respectively, as well. So the first thing we do in these notes is we talk about this little graph, just using that information. I am going to put at least a couple little points here. Oops, sorry about that. So we'll talk about point A, point B, point C, D, E, finally F and G. Now, looking at this graph, we can definitely identify the lowest point. And usually that's pretty easy. I mean, if you have to draw a dotted line, there's nothing wrong with that. But if you draw that dotted horizontal line, there's no other point on that graph that will be lower than where that is. So C is our absolute max. Similar to that, if I look at point F and draw a dotted line, we can see that the function evaluated at F is larger than any other point. Oh, so the problem with making a mistake, it's obvious when you videotape it. That's the absolute minimum, it's the lowest point. And then up here at F, we have an absolute maximum, the highest point. Now, within the graph itself, we can identify where our local mins and our local maxes are. Local maximums are larger than any point nearby. So B and D are both local maxes. And then the problem with A and G is that the function doesn't exist on the other side of A and G. So it doesn't exist, larger than G to the right of G or less than A to the left of A. And so that point at A and G respectively can't be larger than points nearby because there are some missing points. So G is not a local min and A is not a local min as well. But E, on the other hand, is well within that domain, and that would be a local minimum. Now, that leads us into what's called Fermat's theorem, which isn't on the next page here. And it's the idea that if function f has a local minimum or maximum, then f prime of c is equal to 0 or f prime of c is undefined. Now, we have not dealt with the, I'll write it down here just so I can highlight it, that f prime of c, and I shouldn't say is equal to because you aren't, it's undefined, it's not equal to anything. Really, really important that typically, or really in the context of this course, is going to be when we would have f prime of c causing us to have a number divided by 0, basically that indeterminate form. Now, it may be 0 over 0 or infinity, so on and so on, but when we talk about the function being undefined, it is generally, and certainly as we run into polynomials and rationals and trigonometry for that matter, when we divide by 0, that function or the derivative would be undefined at that point. So the remainder of the notes is doing a little bit of this. Basically, what we need to do is find out what C is. And the way that we find C is we identify them as critical numbers. And critical numbers, and this is part of that key terminology section in math, if we want to call it that, critical numbers are when f prime of C is equal to 0, or and maybe I should put and here, it's a little bit better, when f prime of C is undefined. All right, certainly the first one, f prime of C being equal to 0, will occur the most often. Now, really important to read that notation closely. What they've given us in part A is not the derivative, it's the function itself. Therefore, f prime of x is equal to 3x squared plus 12x plus 9. And if we are now identifying when f prime of x is equal to 0, we are essentially just solving this quadratic equation. And the way that we do that is we would factor our 3 out and then factor the remaining quadratic. So we would have 3 times x plus 3 times x plus 1. Very important to have that 0 on the left-hand side. That's what allows us to do the next step. And I hesitate to say 3 because 3 can't be 0, but technically there's 3 factors. So we should think about each factor being equal to 0. So even though it seems ridiculous to write, I'm going to write 3 equals 0. That can't happen, so we're not going to worry about that. But x plus 3 can equal 0. That occurs when x is negative 3. X plus 1 can equal to 0, and that occurs when x is equal to negative 1. I'm going to bring the graph of that function up just so we can make that graphical connection. When we look at the graph of f of x, which is given on Desmos here in red, we can see that it has a local min, or a local max when x is equal to negative 3, and a local min when x is equal to negative 1, and those correspond perfectly to the critical numbers that we found in our notes. We are going to talk about, not today, but something called the first derivative test, which is going to allow us to look at whether it's a min or a max and use information to determine that without necessarily having to graph it. Having your graphing calculator is never a disadvantage, especially in calculus. So definitely exploit that and graph these functions, if nothing else, to verify the work that you've done. Now, polynomials, which is the example we just did, are typically not the problem. Where this gets more complex is certainly, trigonometric later in the course, but rational functions tend to give students a little bit of a problem. If nothing else, you have to remember that critical numbers are when, in this case, and I'm going to write it up here again, that critical numbers for this question is when y prime is equal to 0, because in this notation, y is basically f of x, or when y prime is undefined. Bad commas there, I'm just going to rewrite them a little bit better. So what we need to do then, just like the last question, is find y prime. A couple different ways of taking the derivative of this function. I prefer to use the quotient rule, but if you're comfortable, you could write this as y equals x times x minus 1 to the power of negative 1, and then use a combination of the product rule and the chain rule. But I am going to do the quotient rule because I think it should be your go-to technique. So the way that we do that, y prime is going to be equal to the original denominator squared right away. Then it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. All right, I might write that over here just because it's always nice to see that if I took d over dx of f over g of x, what I would have is f prime g minus g prime f all divided by g squared. That's that kind of function notation shorthand we talked about a long time ago. I mean, chapter 3, right? But it is the quotient rule, very important. Now, we're going to clean this up. It's always best to clean it up. This is then y prime is equal to x minus 1 minus x over x minus 1 squared. I know it's tempting to expand that denominator. Don't do it. Factored form is much better to determine when, any expression is equal to 0. So we're going to have y prime then is equal to, well, x minus x is 0. So we're left with negative 1 over x minus 1 squared. Now, really importantly, the numerator is a constant. So that fraction is never 0. But y prime is undefined when the denominator, which is x minus 1 squared, is equal to 0. Now that's going to happen because the square root of 0 is 0. We get x minus 1 is equal to 0, or x is equal to 1. Now, I want to go and switch to Desmos right now, because if we've done this correctly, that tells us that there should be a local min or a max at x equals 1. Some of you may know the problem already because it's not going to happen. But avoiding all spoilers, here is the function we're looking at. Oh, I'm not going to cooperate on the smartboard. this guy in blue. I'll zoom out a little bit just so we can see what's happening. This function has neither local mins, local maxes, absolute mins, or absolute maxes. But what else is really important to notice is if I zoomed in a little bit, what's happening when x is equal to 1? I can't actually trace that function at that point because as x approaches 1, this function approaches, the limit from the left-hand side is negative infinity and the limit from the right-hand side is positive infinity. Now, the way that we can identify that maybe gap in this technique is that this is not in the domain. It is not in the domain of the original function given, which was y was equal to x over x minus 1. That x equals to 1 is what we typically call a non-permissible value. It's also the location of a vertical asymptote in this case. Because that's not in the domain of the function, this x equals 1 cannot give us a min or a max. It doesn't exist. So it can't be higher than nearby points because it doesn't exist. So in this particular question, we have no critical numbers. So there are no critical numbers. And it's that kind of ever-present maybe hassle that students sometimes experience with math. So we can get one answer, many answers, or it is very possible that we can get no answers. All right, that's the end of part 1. Make sure you check out part 2.